Okay. Am I audible now? Sorry to, I'm just checking again.
Yes, sir.
Thank you. So we'll start the session now. Hello everyone, I'm Sai Venkatakrishnan. I'm a PhD scholar in the Department of Computer Science and Engineering at IIT Madras. So this is week 2 live session in the NPTEL course Operating Systems Fundamentals. For those who are joining the first time, just a quick brief overview of how this live session would work. We would be discussing around 10 questions uh, that were part of the previous offering of the same course in the week 2 of this operating systems fundamentals course. We will be discussing these 10 questions, how to approach the question, what the solutions are, so that you will be better equipped when you try to solve the assignment of week 2 in this current offering of this operating systems fundamental course. This session will be recorded, and also the video, the recording session as well as the slides should be available to you once the meeting is over. So make use of this meeting. Try to be interactive. You can ask doubts, whether it was within the lecture or based on these questions. You can ask doubt, and as much as possible, I'll try to clarify all of them. So this will be a 1 hour session. Okay. Thank you. So we will get started. Okay. So the first question we will be discussing is as follows. In which of the following user interfaces a task is accomplished by executing a file containing commands and directives? Option A, command line interface. Option B, graphics user interface. Option C, batch interface. And option D, none of the above. Anyone trying to guess or know what the answer is? The first question. Okay, Gopal tells option C. Anyone else trying? Okay, one option. Okay, Jainab tells command line. Okay, we have two possible answers then. Anyone else trying to going for graphical user interface? Option B or option D, anyone? Okay. So we will first understand what the question is. So the question states that asks us to find which user interface is usually works in the way where you have given a file and the file contains a list of commands, and these commands should be executed sequentially or parallelly in some fashion, and this is the only user interface that would be available for the user to execute programs or give out orders. So if you have gone through the lectures, there are three types of interfaces that would have been discussed. So one is the command line interface. So normal, if you have used Windows uh, uh, or Linux, there would be a command line interface. So if you just open terminal, for example in Linux, you will get a command line shell, and you can key in commands one by one, or you can run a script or anything, and the output would be uh, given to you. But usually Windows or Linux, it's like a mix of both. Command line, you can access the OS via the command line as also via the GUI. So mostly it's like a graphical user interface. The question specifically states that only by executing a file, the user interface executes commands and directives. So in that case, if you had gone through the lecture, you would have come across this batch interface. This batch interface is nothing but it's a file, and it will contain a list of commands, and those commands should be executed. So for example, say you have if you are being work have experience with SQL or something, usually this batch operations or something they will mention in SQL and those terminology. So similar to that, all these commands should be just present as part of one file. Whatever you want to execute, say you want to execute one command to copy all files from one place to another within the system, and the second you want to rewrite something, rewrite the names present within a file to some other name or something like that, and the third you want to execute a list of programs at one particular time. So all these three commands should be present as part of this batch file. It would be batched together, and at a specific time or something like that, this should be executed, this should be given to the system, and the system would automatically just take this file, execute it. So the user does not need to be manually, like each command he needs to be giving to the system and seeing whether it's getting executed or not. He can just give this file and the system will take care of the rest. So the answer for the first question is batch interface. The remaining two types of interfaces do not work as specified in the question, like given the file and which contains the list of directives or commands. The remaining two interfaces does not work in that sense. So the correct answer is the batch interface. These are all wrong answers. Okay. Any doubts in this question, the first question? Okay, I assume there is no doubts. If you have doubts, you can either unmute or you can just send a message in the chat box. I will. So we'll move to the second question then in that case. So which of the following operating system services helps to manage permissions of a file? Option A, IO operation. Option B, file system manipulation. Option C, communication. And option D, program execution. Any guesses what the answer might be? Okay, option B I've got. Okay, yes, yes. So many of you are telling option B. Yes, that's the correct answer. Option B. So just a quick brief of what the other options would be doing is the services are. If you take IO operation, it's nothing but how the IO devices, what should be passed to the IO devices. Say example, the size of a buffer which has to be printed, etc. Which IO device the OS requires access to, and all those other specific properties which the OS requires the IO device to execute, those things would be mainly the IO operation services. So for example, if you do a printf or a cout in C++, it would go to the standard output device, and that would always be something like your display device or something. So these are the IO operations that the OS services would do. For communication, where it would be used is, say if you have one process P1 and another process P2, and both are executing, and if this process wants to send some message to the second process, what it can do is it can have a shared memory, and this shared memory would be shared between both this process 1 as well as process 2, and it can pass the data. It can just write some data into the shared memory, and process 2 can just read this data from shared memory. So in the later classes, when you read about something called virtual memory and the concept of paging, you will get to understand better how this shared memory is would be implemented. So other ways of communication include you can directly send a message from process 1 to process 2 and via signals or something, and these are all provided by the operating system, these services. So that's what communication is all about. And program execution is nothing but in if you are used in Linux, or if you just do like dot slash a dot out, or even in like any OS, if you try to execute this file in your command line, say this a dot out is the executable that you get when you compile say a hello world file h.c, the C program file, and you get this executable a dot out. And when you execute this specific file a dot out, the binary file which you get after compiling, what happens underneath is nothing but this dot slash a dot out will invoke some services in the OS, and those services would do what it would do is it would create some memory for this binary to be loaded into from the disk. So from the disk into the memory, the a dot out binary file would be loaded in, and it would be all the variables, all the stack, the heap, the stack, especially the stack, and those things would be set up, and it would be given back. Control would be given back to the main function, which is the like usually the starting point in any C program file. The control would be given to the main function, and then the program would start executing. So when you just directly do this dot slash a dot out, there is so much of things happening underneath which the OS does. So what it does, it starts a process. So this a dot out is nothing but a binary image. It will instantiate that as a process, and then it will create some memory for that process. It will initialize all the parameters. Say like if when you just do C out hello world some message, right, what this C out would be. So those things all the operating system should initialize before it starts executing that binary a dot out. So all these things the operating system would initialize and then give back the control to the user program, and it will start executing from the main function, which the user would have coded in the program file. The main function would be to find the Fibonacci number or something. So from there the execution will continue. So this is what the program execution service is all about with respect to the OS services. Finally, coming to the answer, our actual answer, file system manipulation. The file system manipulation is all these things, right? The a dot out binary file, whatever I have specified. So those things all are stored in the disk only by default. That's the secondary storage. So all these files and all these things is something like an abstraction provided by the OS so that the user can easily organize the information whatever is trying to act upon. So the notion of directories like slash home directory, you have a slash music directory. So all those things are something that the file system would provide to the user. So the file system provides the user with some abstraction, some API, which the user can make use of to arrange whatever information he wants to access in files and directories, and also provide some properties like some files, say you have some password file, it is to be very secure and no one should tamper that password file. So that password file can be given a permission like read only or something like that, so that no one else can write into that file. And also it will have other permissions like who is that specific owner of that file, whether that specific user, say you are having a multi-user operating system, where user 1, user 2, everyone has is using that same system, or they can access that system simultaneously. But the password file should only be accessed by the user 1 only. He's the admin. So in that case, you can set the file permissions, all those things, such that only the admin or the user 1 can access that file. So all these things, all these features should be provided by the file system manipulation. Okay, so these are all some set of the basic services provided by the operating system, and which is crucial for you to run to do something like in a day-to-day life with the operating system. So if you notice, like when you just run this dot slash a dot out command in your terminal to run a C file, that C binary, you would be using all of these OS services. So you would be using the IO operation to print something onto the screen. You would be using this file system to first of all access this binary file which is stored on the disk. You would be using the program execution tools services given by the OS to execute this binary and execute your main function. So all these services you would be using simultaneously. The OS would be providing these services, and these are all crucial so that the OS achieves what the user wants to do, helps to achieve what the user wants to do. Okay, so any doubts in this question? So if there are no doubts, I will move on. Question 3. Which of the following operating system services helps to provide debugging abilities? Option A, resource allocation. Option B, IO operation. Option C, communication. And option D, error detection. Anyone trying to answer? Whether it's option A, B, C, or D? Okay, option C. Someone tells. Okay, let's see. Communication. Okay, some tell option D. Okay. Anyone else trying to option D? Okay. So two of them with option D, one with option C. Okay. Okay. Yeah. So let's understand the question first. The question asks like what specific OS service is used to provide debugging abilities. So by debugging abilities, what we mean is when we say that a process has stopped executing, there can be multiple reasons. So say you whenever you try to execute a C file, you usually get some error message like segmentation fault. So this is one common error message that you will get whenever you first start coding in C program. Say for example you have an array of 10 elements, and by mistake if you access the 100th element of the array, sometimes what it happens is it will not it will result in a segmentation fault. Excuse me, sorry. Sorry for the disturbance. Yeah, so if you access the 100th element of the array beyond the size what you have allocated for this integer array, which is just of 10 elements, if you access say the 100th element, you will result in an error. So those things are all like will be are like segmentation fault. So the errors can be of multiple types. Say you might result in the error might be like the whatever memory you are trying to access. Say you are doing some star of pointer, you are trying to access one memory, you with the help of a pointer operation in C, and that memory is not part of the virtual address given to the process by the operating system. Okay, so it's not mapped. When you later come across this virtual memory concepts, you will better understand this. So just giving a brief overview. So if you try to access some memory which the OS has not allocated to the process, then it will result in an error. If you try to execute some instruction or some memory which is again not allocated to the process, then again some it will lead to an error. Say if you try to divide by 0, so somewhere you're executing some computation, some numbers you are multiplying and dividing, and in some part of your logic, it turns out that there is this operation, say 11 divided by 0. In that case, it will, if it's not handled properly, this operation, it will result in an error. So all these things should the OS should take care of, and it should properly intimate the user. It should provide the user why that error has occurred and all those things. So that these specific things would be provided by the error detection service provided by the operating system. So for this specific question, the debugging abilities is the correct option is error detection. The other options like IO operation and those things are all not directly related to debugging abilities. They might be part of, but the notion of IO operation or resource allocation or communication are not just used for debugging abilities. So resource allocation is nothing but say your CPU. So how much time the specific process P1 has to execute on the CPU, whether it's for 10 seconds. And once this 10-second time is over, the OS has to shift the execution to some other process P2. It will give the control to P2. So all these resource allocations, and what if both P1 and P2 process tries to uh, access the same IO device, try to use printf at the same time, who gets access to which device first. All those things the OS has to do via resource allocation and scheduling. So that's what resource allocation is. So that's not related with the debugging abilities provided by the operating system. So the answer for this question is error detection. So any doubts in this question? Okay. So just a point to add, this the communication part, right? In some cases, what would happen is, say if you are running P1 and you are having P2, there might be a case where this P2 would be trying to help debug P1, the process P1. So say like you're going, if you had used a GDB or something, there are cases where you can try to attach two processes or something like that. So not going into depth, but the second process can be used to monitor what process one is doing and what error is occurring. So this is, it uses communication services of the OS underneath, but this is not directly related to the debugging ability. So this question specifically asks for the OS services which helps to provide debugging abilities. So the answer has to be error detection, option D. Okay. Yeah. Any doubts till now? If no doubts, then I will just I will move ahead for the fourth question. Okay. So the fourth question is as follows: instead of direct system calls, it's like a fill in the blank. So instead of direct system calls, dash prefers system calls, which is written in dash. So the option A is like low level API prefers system calls, which is written in low level language, or the high level API prefers a system calls written in high level language. Low level API written in high level language, or the opposite, high level API prefers system calls written in low level languages. So any guess what the correct answer is? Okay, option D. Okay, so some tell option D. Option D. Okay, option A. Yeah, I'll just circle the possible options that you are telling and we'll see what the answer is. So I've got two options till now, option A and option D. Anyone else going with any other options? Option B and C, any takers? Okay. So first, let's understand the question. What they mean by direct system calls is by so how are these system calls in the first place written? How are they designed? So by system call, what we mean is there is the OS residing at this in the kernel space, and you will have some process which is executing, and this is the user space, and you have the full OS. And say if you want to access the read system call, and how this read system call would be implemented in the actual thing is, this read system call would be provided a ID or number by the operating system. So let's say like this number is 20. So what now the process 1 has to do is, process 1 what has to do is, in order to execute that system call, it has to first uh, set the parameters whatever it has to pass to the read system call. For example, the read system call, if you do man read, which is just it will just display that manual page for that read system call. If you are in a Linux system or Unix, it will display the read systems yeah, that read system calls manual page. So for example, that read system call is nothing but you are reading from some device. So the parameters should be the function parameters. What the system call expects is the pointer and also the number of bytes it has to read from which device, whether it's from the standard input device or from some other device, something like that. And those are the common parameters that the read system call expects. So all these parameters should be passed to the read system call in some way via registers or via memory. So those things should be set by the process P1 first. And second, what it should do is it should call the OS. It should stop executing. So process P1 would be executing, say, in the main function or something. It would stop executing and call the OS and inform that I want to execute this read system call, provide me that service. So for that, what the process one would do is it would say it would one simple way is it would set this number 20, which denotes that read system call, which is part of the operating system. It would load that 20 number into a register, say R1, and it would execute an instruction call syscall or something, which would stop executing that process. It will raise a trap. So this is like a trap instruction. So as if some error had occurred or something, it will raise a trap, and that trap would be caught by your trap handler or the interrupt handler. by your architecture. So in week one, you would have studied this interrupt handler and those things. So this trap handler will catch this specific trap, whatever was raised by your process P1, and on seeing this register R1, it will get to know that okay, this specific process P1 is trying to uh, invoke some operating system service. So what it will do, it will see this number 20, and it will get to know that this read system call is being invoked by the process P1, and it will transfer execution to the read function. It should be present within the operating system code somewhere over here. So this read function would start executing. So these many, so this first step and second step and all these things has to be executed by the process one. So by low level API, so the question asks us like to execute all these system calls, to invoke these system calls, and whatever has to be done, whatever has to be set up to execute the system calls, which method is preferred. So some of you have told it's like low level API and low level language. Some of you have told high level API and low level language. So by low level language or low level API, what you mean is actually assembly code. Okay, you just key in your assembly code. It's just like move instructions and afterwards jump instruction like that. And by high level languages, what you mean is actually the C code or the C++. So usually it's C only in respect to OS, mainly Unix if it's C. So in that case, you have mentioned like low level API prefers low level language, high level API low level language. So the correct option actually is option B. High level API prefers system calls written in high level languages. The the understanding by why this option is correct is that if you see from the point of how we manage the OS, say for example, this the same read system call. If you want to add an extra parameter, say I want also to add a parameter that specifies what the color of my input should be, or say if I don't get any input, what the default input should be that should be returned by the OS. Some extra parameter you have to pass to the read system call. So in that case, if you have if you had been using a low level API and a low level language, what would have happened is that to change the implementation, it would have been very difficult because in your implementation, it would be like move instructions and all those things and jump instructions which are hard coded assembly, and to change those instructions and to manage those instructions would be difficult. So this, if you have been doing this in a high level language, say C or these things, it would be very easy to easily extend or change the implementation or parameters whatever the read system call expects. So that's the advantage provided by the high level languages. It gives a way of systematically way of like an easy way of implementing, as well as not that much decrease in the speed. So C is like very close to the hardware, the C language. It's very, you can embed these assembly instructions also within the C language. So C language as such does not affect your performance in any case. So in that case, usually it is preferred to implement these system calls and all these things in a high level language interface instead of directly encoding the logic in the assembly code. And by high level API, what is generally meant is this read system call. For example, say uh, this read system call, you are having currently, say it is being having some ID, say 20, right? 20 we had used it before. and later on that um, read system call changes to 21 due to some changes in the operating system. In the next version of Linux, say that specific system call ID for read, which was assigned to that read system call, is changed to 21. In that case, what happens is, if you had hard coded this 21 as part of your process P1 itself in that user space code, whatever you had written, if you had hard coded, then you would have to change all the sorry, if you had hard coded this 20, okay, if you had hard coded the previous ID 20 within the process P1, at all places you should change this 20 to 21 so that properly that read system call would be executed. But if you had used like a API sort of like an abstraction, where this process P1 would invoke some function, say like read something user space, and within this lead user space is something which is like a shared library or something, okay, and this shared library would contain the actual interface and the ID whatever we had discussed in step 1 and step 2, the setting the parameters and calling that specific, oh, the setting that ID system call ID 20 or 21 in that register, and then invoking system syscall instruction. Those things all this read underscore us function would be doing. So my process as such, my user code does not need to know what the read system call um, internals are, or how the arguments have to be passed exactly in which way or something. It just has to call this read underscore us function, and the read underscore us function will take care of the internal details and call the corresponding system call. So in this case, whenever I have to change the read system calls in ID or something, my user code does not need to change. So that's the advantage of having like a high level API and also a high level language while implementing these things. So any doubts till now? Okay, hope you understood these things. Thank you. In that case, we will move on to the fifth question. So the fifth question is as follows: which of the following parameter passing method has a limit on the number of parameters being passed? Option A, block method, where the parameters are stored in a block. Option B, stack method, where the parameters are pushed onto the stack or popped from. And option C, where the parameters are directly transferred to registers. And option D, none of the above. So any guesses which might be the correct answer? Option A, block method, or stack method, or the register method, which has a limitation on the number of, okay, some one are telling option B, which is the stack method, okay. Any other options? Option A, block method, okay, it will have a limitation on the number of parameters being passed, okay. Anyone else? Option C or option D, any takers? Okay, let's understand what they mean by parameter passing and this number of parameters being passed. So as I mentioned, for example, when you have this read system call, if you look at that manual entry of the read system call, it will tell what parameters needs to be passed to execute that system call. Say a pointer to the file, the number of bytes it expects, and all these things. Okay, so say this read system call expects two parameters. Different ways are there to pass whatever information the user process has to pass to the operating system, the kernel space. So one method is this block method. So by block method, what it does, it stores everything in a block. So this block can be say at some address, some memory location within the user space, and what the user will do is it will pass the pointer to this block to the kernel space. The kernel, what it will do is it will it will just get this pointer, and it will know from this address location all the parameters it needs access to for executing that system call. It will get it can read from this block, and it can continue executing that system call in the kernel space. Now in this block and in the stack method also, instead of passing all these parameters in placing it in some memory location or block and then passing the pointer to the kernel space, what the user space should do is, by default there would be a stack, the user stack that would be executing your return address, all those things would be pushed onto this stack. In the same stack, what the user process excuse me, what the user process would do is it will just push the parameters like p1, um, p2, p3, all these parameters it would be pushing onto the stack, and it need not pass the pointer also, because the OS as such, it can just look at the stack pointer register and get to know where the parameters are placed, and it will just read from that, from these memory locations, the corresponding parameters and execute the system call. Now in both the block and as well as the stack method, if you see, what the user can do is, as one of the parameters, default parameters passed to the kernel space, it can specify the number of parameters it is actually placing it in the block or the stack. So that zeroth argument, whatever it is pushing into the stack or placing it in the block, can be the number of arguments. So in a way it tells the operating system, here I am going to pass you say 10 arguments or 20 arguments, and up to say like parameter 1, parameter 2, like that up till parameter 10 you can expect, and the number of parameters should also be passed to the operating system by placing it in the at the start of the block, at the start of the block. So in a way the OS, the user space informs the OS how many parameters it is passing. So that's the advantage with this block and stack method. So if the user wants to pass 15 arguments or n number of arguments, it can just specify that number, first 15 or something it can specify, and can place all those arguments up till parameter 15, argument 15, and pass to the OS. So in block and stack method any number of parameters can be passed, but there's option C, right? If you notice, option C is the correct answer, as in it limits the number of parameters being passed, because in option C you are using the registers. And if you recall week 1's lecture, uh, the registers are the fastest memory space present in your system, and is present within your CPU itself. And this memory number of registers should be limited, like say 15 or 16 registers. So out of these 15 or 16 registers, you can use only say in modern systems, you can use only like say 7 registers or 8 registers, or maximum, if you even if you want to use all these 15, all the registers, there are only 15 of them. So more than 15 you cannot pass any parameters via this register method. So that's why there is a limitation, the number of parameters that can be passed via these registers. So any questions in this, any questions? The answer is option C, because the count of the registers are self limited in a system, and it places an inherent limitation on the number of parameters that can be passed from the user to the kernel space using these registers as medium. So any questions? Okay. In that case, let's move on with the sixth question. So question 6 asks us, So fill in a blank. Which allows the OS to run on non-native hardware? Option A, emulation. Option B, subsystem. Option C, daemon. Option D, none of the above. Nandan, I'll just come to your question once I finish this question 6. I'll answer yours. Just a second. So, can anyone tell what the answer for question 6 could be? Can anyone guess? Okay, option A. Okay, yes. So option A is the correct answer for question 6. So the other options are like irrelevant for this question, and it's just for namesake the options are filled in. So emulation is the correct answer. Say you want to execute say ARM ISA that some binary which is having ARM instructions on x86 hardware, Intel hardware, then you have some sort of emulation software which should for usually for testing cases or something, you would run this ARM binary on the emulation software to see whether it's executing properly and all those cases, all those instances before you try to actually run it on the ARM system. So emulation is an important uh, software component, and it usually allows the OS to run on non-native hardware. Yeah, so option 6 is the correct answer. Okay, so I've got a question with respect to the previous question that we have discussed. Do we use the stack method every time? If we have less number of parameters, is that advisable to use the register method? Yes, Nandan, that's a good question actually. So as you had mentioned, we usually do not use the stack method always. So this register method is the preferred way of usually communicating these parameters from the user space to the kernel space, because you you just say want to pass 4 parameters from your user space to kernel space, and in that case you just fill in R1 to R4 registers with these parameters with those values, and you don't do anything else. You just call syscall with that specified system call ID for say read system call or something, and the kernel space starts executing. But the only thing is that you should make sure these registers are not being used by that kernel until the time that kernel reads those registers. So until the time these arguments, whatever value you are passing via these registers, those should be properly read by the kernel, and it need not access any memory address, or it need not access the main memory or cache, nothing it has to access. It just has to access these 4 registers to read the arguments that you have passed from the user space. So in that case, the registers method is the fastest method for access passing these parameters. Only if the length goes beyond say 5 or 6, the stack or the block method is being preferred. In some cases what happens is, say you want to pass say 10 parameters. So in that case the first 4 would be via the registers, and the next 6 what you will do is you will pass a pointer to the next 6 registers that will be placed on the stack or the block. So it's like a way of like a trade-off, or it's like an optimization. So maximize as much as possible the parameters that you pass via the registers. So combination of these parameter passing methods can also be used in your operating system, in your language thing. So it all depends on what the design choices are, whether it wants speed or whether it wants flexibility. All these things are there. So hope that answers your question, Nandan. Yeah, thank you. So in that case, we'll move ahead to the seventh question. Okay. So the seventh question is as follows. The Unix OS is option A consists of system programs. Option B, the Unix OS is a kernel that contains everything below the system call interface and above the physical hardware. Option C, The Unix OS provides the file system, CPU scheduling, excuse me, memory management, and other OS functionalities. And option D, all of the above. So any answers on this? Option A, B, C, or all of the above? What the Unix OS represents? What does it contain? What does it do? Okay, option D. Okay, one is telling option D. Let's round it. Any other option which might be correct? Okay, option D. The other one also. Okay, option B. Okay. Option A and C. Anyone? Just A and C. Okay. So if you have gone through the lectures, the lecture videos, okay, B is wrong. Okay. So C. Okay. The correct answer is actually option D. That is all of the above. So the Unix OS is nothing but so option C is the various OS services that the Unix OS provides, that the file system, CPU scheduling, memory management. So option C is like partially correct as it's option C, and the Unix OS is the kernel space, right? So whatever is below the system call interface, if you notice, this system call interface is nothing but the which is present in the user space. Whatever is below that and above the physical hardware is the kernel space. So whatever is in the kernel is the operating system. So option B is also correct, and option A is nothing but so some system programs are there which help facilitate the user to efficiently run programs, execute programs, and use the system. So those system programs, for example, say your so something which checks whether your disk is running properly, or something like a linker, or something like the system call implementation itself. So those things are also packaged as part of the operating system. So in a way, all the options are correct, A, B, and C. So that's why the correct option is option D, all of the above. Gopal, you have asked a question. Does it has a hardware? Can you just explain the question again? I didn't get it. So does it has a hardware in the sense Unix OS as such does not have any hardware or such. So this Unix OS runs on the hardware. So I guess you meant by that. Can you just comment in the chat message if the thing is cleared? So as part of the Unix OS, the hardware is not part of the Unix OS. So whatever is present above the physical hardware, so your user space is over here, which is the programs that you are running, the applications. Next is the OS, and followed by that is the hardware. So the user has to communicate with the OS, so in order to use the hardware efficiently. So the OS main functionality is that. So hope this answered your question, Gopal. If else, you can just comment in the message. In interest of time, we'll just move on to the next question. If you have any doubts, just feel free to comment in the message or unmute yourself. I will stop and answer your questions. So question 8 is as follows. An operating system which is divided in multiple modules has which one of the following is correct? Option A, it offers the advantage of not getting affected fully when one module is changed. Option B, it comprises the kernel with all the modules. Option C, it provides more flexibility and functionality to each module. And option D, all of the above. Any guesses? Anyone trying to take answer which option would be correct? Option A, B, C, or D? So, okay, Nandan tells option D. Anyone else? Option A, B, or C? So divided in multiple modules means it's like the correct term for this is like uh, microlithic architecture. So one is the monolithic, so in which like everything is placed in the kernel in a single module. So if it's divided into multiple modules, your kernel, it's like a microlithic architecture. So if you had gone through the lectures, there have been mentioned microlithic architecture, since it's like module 1, module 2. Any changes that you do to module 1 would not change the module 2. So in a case, it is easy to maintain and the functionality or the implementation whatever for module 1 separately without affecting other modules which are present. So this module 1 can be your file system module. This module 2 can be something like say uh, security module, and this the other module can be say like a message passing module. So like that you can split your kernel into multiple modules and make them independent of each other. So it gives the OS designer the flexibility to change the implementation at any time without affecting other modules. So if he wants to change the file system implementation, he need not go and touch the he need not go and touch the other modules. So it can be left unchanged. So that's the advantage. And also from a security perspective, if say an attacker or some hacker tries to, not the word hacker, but the attacker tries to attack the system and say corrupt your file system, tries to get hold of the file system module, he cannot go and affect the security module or the message passing module. So all these things would be separately would be separate, and it don't affect each other. So that's the advantage of this microlithic architecture. Okay. Any doubts in this question? Um, we'll just finish the other two questions in say maximum 5 minutes, 5 to 7 minutes. That's it. Sorry for the delay. Okay, so Nandan has asked a question. Despite the advantages for microlithic architecture, any reason why Linux is monolithic? That's a very good question, Nandan. So these are the advantages of microlithic architecture, but the disadvantages are um, you would need like the message passing primitives. So one is like you would need message passing primitives to for communication between these modules. So by the term, when we tell like these are in multiple modules, right? They don't share any memory between them as such. If you say monolithic architecture like Linux, all those 30 million, or like, I'm not sure of the count, but it will be millions of lines of code. All those millions of lines of code would be present in your kernel space. But in a microkernel, your module 1 would be present in a separate address space. Your module 2 would be separate, like that. And to interact between these things, you would be passing messages between them. And by message passing itself, there, so in the microkernel also only like some part of the operating system, the crucial part would be would be like in the kernel space actually. So for example, whatever is very crucial, say your paging, or only like 3 to 4 services, whatever the OS deems to be crucial, whatever the OS designer deems to be crucial, would be part of the kernel space, and the remaining whatever the services that the OS offers, say the security module or the file system module or something like that. Those things are all would be implemented as modules, and your user process, say P1, has to interface separately with these modules, has to contact these modules and get the services. So in a way, this is different from the way the Linux, the monolithic architectures work, and it would affect the usability, the general ease of usability. So that is a major like the learning curve, the stepping stone in adopting these microlithic architectures. And the time when these Linux, in my opinion, right, when these monolithic architecture, the Linux OS or these things, when they were developed and implemented, so it was the 2000s or something, right? So 1995, from that time itself, if I recall correctly. So in that case, these notion of security and those things were not much. Um, they were not very uh, researched at that time. They were not, see, once this internet came up on the internet boom and the web boom, all those things, then only the attackers would be using the internet itself to get access into some system, make use of the exploits, the bugs present in your user space, kernel memory, all those things, and get into your system. So in that case, it was too late to switch from this monolithic to microlithic architecture. If you are interested, I can tell, like, so there is a specific microkernel thing like cell 4. From a security perspective, this is very secure, but and it's also like verified. So verified in the sense it don't have any security bugs at all. It's fully secure and it's verified, like mathematically it's verified. But the time it takes to do this verification and also to design these microkernels is somewhat the usability is somewhat less than these monolithic kernels. So that's the one reason I feel like these microkernels, this type of architecture is not uh, adopted mainly in these things. Yes. So moving on to the ninth question. Hope that answered your question, Nandan. I will just add a slide also at the end once the like meeting is over. Um, have it with the answer for this specific question, because this question is really nice and it would be good if I include that slide with the answer also. I will add that and upload the slides. Okay. So the ninth question is as follows. Memory management activity does not involve the following. So one, keeping track of which part of the memory is currently in use and by whom. B, deciding which process and data to move into and out of the memory. Option C, suspending and resuming processes. And option D, allocating and deallocating memory space as needed. So any guesses what the correct answer would be? Which one of the following is not part of the memory management activity? Option A, option B, C or D? Okay, option C. Okay. Anyone else? So memory management activity, in the sense it has to determine, it has to optimally use the memory, that the main memory that is provided in the system, and allocate the main memory between all the processes and make sure that the memory is utilized properly in an optimal fashion. So for that it has to, of course, decide what process has to be moved in, the data has to be moved in and out of the memory, and also has to track which part of the memory is used by which process, so that your some process cannot use the other process memory. It's not allowed. So option A and B are indeed memory management activities, and option D is the basic activity, allocating and deallocating the main memory space. So option D is the correct answer. That is, suspending and resuming processes are not memory management activity, but it's part of the process management activity. Okay. Moving on to the last question. Which of the following is not a task of file system management? Option A, backing up files onto stable storage media. Option B, optimizing and deciding which file data to be stored in memory. Option C, primitives to manipulate the files and directories. And option D, mapping the files onto secondary storage. So which one is not a task of file system management? Any guesses? Anyone knows? Anyone trying to answer? Option A, B, C, or D? Okay, option A. Okay, one one of them are telling option A. Backing up files is not a task of this file system. Okay. Yes. Anyone else going for any other option? B, C, and D? Okay. So the correct answer is actually option B. So that's the correct answer actually. The reason being, so optimizing and decide. So what are the tasks of the file system? So one is it has to the mapping the files onto secondary storage as mentioned in option D. So this is one uh, task of the file system management. So that notion of files and directories. So this is part of the file system management. And the second thing is it has to uh, so this is option C as well as option D. So option C is this files and directories, and option D is it has to store these files onto the storage medium, the secondary storage. So that has to be done by the file system management only. And option A is backup files onto stable storage media. Okay, so this answer is sort of tricky. So in a way, if you want to see, right, this backup files onto stable storage media, in your system usually if you see this the main memory, and you will have the secondary storage. So this main memory would be would be volatile, and the secondary storage would be non-volatile. So in that case, right, whenever your main memory is having some, say you're writing some file, and that file is being allocated in this main memory, some contents, and say suddenly you're saving it, you are using like control saving that file in your text editor. In that case, what should happen is, before say some power cut or like the power goes off from your system, it is crucial for this content whatever you are saving in the main memory, it has to be stored in your file also, in the secondary storage medium. So for that, what happens is it has to be returned to the file and permanently, because this main memory is volatile, and once the power goes out, the power supply to that memory device, all the memory would get erased within a few seconds. So before that happens, it has to be returned to your secondary storage, and this is via the file APIs and all those things. So that's what they mean by backing up files onto stable storage media. The option B actually is optimizing and deciding which file data to be stored in memory. So what option B is actually, you have say some file over here present, and it has to be used by some process P1. Say this is file 1, and P1 wants to use F1, and say this. this actual usage would occur at some time in the future, say after 10 or 15 minutes only. So if the OS operating system gets to know this, right, then in that case, for the first 15 minutes, it need not bring this file into the main memory to be used by process P1. Only after the 10 or say 12 minutes, it can get this file into the memory so that P1 can use it at that specified time. So in that case, it optimizes when this file has to be loaded into the memory, the main memory from the secondary storage, such that the process can use can load the contents and manipulate the contents like that. So this specific option B, right, deciding which data has to be got into the main memory, is something to do with the memory management system and not the file system. So that's the answer. So this option B is not part of the file system management. It's part of the memory management system, part of in the operating system. And the other thing to note is you might get confused when you just read option A, that is like backup files onto storage media, because usually the backup process as such would be like some third party application, and you would be like enabling that application to back up your files or something. But the way the option A has to be read in this context is when you temporarily change or write something into the main memory, it has to be definitely stored in the secondary storage medium also. So that's why this word is clearly written. So in that context, this backing up files on the stable storage media is a necessary operation that has to be done so that you don't lose out any information which you had just told on the main memory when the power supply goes off. So that's the whole notion, the concept of this option A. So the answer is option B. The remaining are all file system activities only. So any questions in this question or the previous questions that we discussed? So if not, then we can conclude this session. Yes. Thank you so much for attending the session and for making it interactive. Sorry for the 15 minutes delay actually, uh, but hope you enjoyed this session, and we would be meeting at the same time next week to discuss the week 3 assignment questions. Thank you so much. Thank you. Thank you, Raja. Thank you, Nandan. Thank you so much.